Hi, and welcome to the NSF workshop, New Frontiers of Thermal Transport. This workshop has been in the making since October 2019. Initially, it was planned as a face-to-face event in March this last year, here at the University of Central Florida, a university that has seen unprecedented growth in the last 20 years and is destined for a great future. However, as you know, COVID-19 flipped the table on us, and we had to postpone the workshop at the last minute. In early mid-summer, we restarted the planning of this event, and here we are, 9 months later, after the original schedule, participating in this 6-day virtual workshop. We believe that setbacks provide opportunities to excel. And specifically, we believe that this event will be more impactful than the originally planned. Instead of 150 participants, there are about 430 now. We were also able to convince several additional world-class scholars to join our panels. A large group of students are attending the workshop this time, and finally, the number of posters is now 114 instead of about 25. The first 5 days are broken down into 3 segments: panelist presentations, social networking and poster session in Gathertown, and breakout rooms. Each day is dedicated to one topic, for a total of 5 topics: artificial intelligence, thermal management, health in the first 3 days, manufacturing and energy in the second part of the workshop. Finally, we will wrap up the last day with reports from the breakout sessions and program manager panels. The 3 organizers, Dr. Jonathan Malin. Jonathan, please say hello.
Hi, everyone. Thanks for being here today. I appreciate being involved in the planning process, and I'm thankful to work with Yoav, Julin, and Ying to plan this event essentially twice. I look forward to a successful event and hearing what the panelists and moderators have to say.
And Dr. Shulin Wan. Shulin, please say hello in a couple of words.
Sure. Hi, morning, everybody. Welcome to this workshop. This is Shulin Wan from Purdue University. Really glad to be a co-organizer for this workshop. And thank you, NSF speakers, moderators, for joining, for your efforts, and I wish great success of the workshop. Thank you.
And yours truly are extremely indebted to the people who work behind the scenes. A special thank you to Ms. Marisa Ramicchio, who has worked day in and day out on so many fronts. Ms. Clarice Quint, who worked with Marisa to develop the website and Gathertown, including the poster sessions. And to Ms. Noreen Hodop, who helped with many of the logistics. And of course, to the panelists and moderators who have put much effort to ensure thoughtful and structured panels and breakout sessions. And finally, to all of you, the participants. On a different note, this year we lost a very special person who was in the forefront of this community, Dr. Avi Bar-Cohen, a luminary heat transfer scholar. Many of you knew him personally, and his loss will be felt for many years. Alav Shalom, may his soul rest in peace. We hope that you will enjoy the workshop, learn something, and more importantly, help in the development of a collective vision for the future of research and development of our heat transfer community. I will now give the floor to the person who envisioned this workshop and empowered us, the organizers, to bring it to fruition. Please welcome Dr. Ying Sun, Program Director, Qubit Division, National Science Foundation. Ying?
Yeah, thank you, Yoav. Welcome, everyone. How are you? I'm Ying Sun, Program Director of Thermal Transport Process at NSF. Some of you may remember the last NSF workshop on Frontier in Thermal Transport was in 2007 at University of Connecticut, and was quite a successful one. After more than 13 years, we're gathering today to develop a shared vision for our community for the next 10, 15 years. I appreciate the organizer, Yoav, Xiuling, and Zhang for their incredible energy drive and vision to make this event happen. Then they had to plan it not once, but twice. Thank you all the panelists, moderators, and participants, and NSF, and UCF staff for your contribution. I'm so looking forward to learning more from all of you. Enjoy the conference. Thank you, and back to you all.
Okay, so now I will ask Matteo and Jan to start their panel.
Okay, thank you, everybody. I will introduce today's panel. So today we will have 5 speakers who will give us talks on the topic artificial intelligence, quantum computing, and data science. Each speaker will have 10 minutes for the presentation. We ask all the audience to stay mute during this time and only ask questions through the chat function on Zoom. We will collect your questions and down select some questions for the afternoon's question and answer session. Well, if time permits, we will have 10 minutes at this morning session for some high-level question and answers between the panelists and the moderators. So at the end of this afternoon session, if time permits, we might give the audience the chance to ask questions in person. So we will now start with our first talk given by Dr. Jeff Snyder from Northwestern University.
Okay, well, thank you very much. So I am Jeff Snyder from Northwestern University. I have been working on thermoelectric materials for about 20 years. And so I'd like to thank the organizers for allowing me to come and express our interest in engineering of complex materials for thermal conductivity, because having low thermal conductivity is so important to thermoelectrics. I am in no way an expert in data science, artificial intelligence, or machine learning. So let me quick describe our interests in thermal transport and then maybe ways how data science can help us understand thermal transport in complex materials. So what initiated my interest in complex materials was the fact that the lattice thermal conductivity, which is so important for thermoelectrics, decreases dramatically when the complexity of the unit cell is increased. And so these are examples of very large complex materials where the complexity is measured by the size of the unit cell. And you can see that some of these materials with very large unit cells have very low thermal conductivity, and that makes them great thermoelectric materials. So a simple explanation for how that happens, how the lattice thermal conductivity can be inversely proportional to the volume of the unit cell, is simply by taking a first order approximation that the heat is carried by acoustic phonons, which travel like waves, as opposed to the optical phonons, which we'll talk a little bit more about later. But one explanation would simply be that the velocity of these phonons proportional to the slope of the dispersion relation is clearly quite high for the acoustic modes and much lower for the optical modes. And so as we get to a large unit cell, we see that there's only 3 acoustic modes per large unit cell, but there are many optical modes, and many of them have become very flat, and that reduces their velocity, and so they transport heat much slower. And so by approximating them as not transporting heat at all, we can explain a volume dependence for the thermal conductivity. Okay, so then another example is that in complex structures such as amorphous materials, one sees that the temperature dependence of the thermal conductivity can be very different. So for crystal material, we get the normally 1/T dependence, but in amorphous materials and also these complex structures, we get a relatively temperature independent. So something is clearly changing in the way heat transports in complex materials. So one of the things that we've been thinking a lot about recently is this idea that the thermal transport is not simply by classical phonons, but we should think of them as being separated into propagons, diffusons, and locons, according to the nomenclature of Allen and Feldman. So where a propagon is a wave-like lattice mode that looks like a traditional phonon, and a locon is a localized atomic vibration, thinking about a local, maybe Einstein type mode, that much of the heat in complex materials is transported by diffuson, which is much larger than a locon, but has an eigenstate which looks very different from a traditional wave. It's very diffusely scattered throughout the material. So the way we like to think about it is that phonons, or now more specifically propagons, travel ballistically. A heat pulse travels proportional to time using a velocity, whereas diffusons transport their heat diffusively by transporting the energy from handing the energy over from one mode to the other, as opposed to traveling it with a velocity. And so then the heat ends up traveling like diffusion through square root of time. So it's been found, the diffusons have been found mostly computationally. So originally by looking at amorphous materials, but now more recently, diffuson type transport can be found even in crystalline materials with disorder. So this is a disordered crystalline material that particularly at high temperature, the diffuson contribution can be very large and even dominate. So the way we like to think about diffuson is that it's diffusive transport as opposed to the traditional phonon method, with thinking about a velocity and a mean free path, whereas diffusive transport, we need a diffusivity where we think about the attempt frequency to go 1 unit of distance, so that's the a squared term, and then you have a probability. In this Ioffe-Regel limit in between the two, we get very similar estimates for what a thermal conductivity should be. For example, a maximum diffuson thermal conductivity is quite similar to the Cahill model, which works well for glasses. And so we think that engineering to a diffuson limit could be a good lower limit for thermal conductivity. Okay, so another thing that we think is interesting in the new, so new and interesting in thermal conductivity has to do with interfaces and boundaries. And just as a reminder, at low temperature for single crystals, we know that the thermal conductivity behaves like T cubed, which can be explained by scattering from the size of the crystal itself. But for polycrystalline materials, we've been using the same type of scattering, boundary scattering model for decades, even though if you look carefully at polycrystalline materials, the temperature dependence behaves more like T squared. And so we think this has something to do with a different mechanism for interfaces and boundaries than the simple Casimir limit that we've used frequently in the past. So in our group, for example, we think that there's a dimensionality crossover such that at very low frequencies, you get a interface type scattering from a two-dimensional surface that was frequency independent like we expected before. But at higher frequency, there's a dimensionality crossover to that reflects the nature of the interface in a grain boundary, for example. So in material science, we know that low angle grain boundaries in particular can be described by periodic arrays of dislocations. And the dislocations are one-dimensional arrays, one-dimensional defects, not a two-dimensional interface. And that leads to a frequency to the -1 behavior of the transmissivity, which we think leads to a dimensionality crossover in the behavior of the scattering and transmissivity of phonons at interfaces. Some hint that this appears experimentally is in Austin Minich's work, looking at the transmission coefficient as a function of frequency in a variety of different materials. Okay, so another point that we think is important is at high temperature, we see our thermal conductivities get very low, and this is again very important for thermoelectrics. And traditionally, we interpret this as a scattering effect, usually due to boundaries or impurities of some sort. But the nature of the thermal conductivity reduction seems to be fairly equal even at high temperatures, which is more akin to a softening type mechanism. So a reduction of the speed of sound that we see experimentally, we'll see in a minute, or basically the speed of the transport as opposed to a scattering. A scattering should have very little effect at the high temperature. So we've seen a softening effect due to a strain in a material. So by adding strain to lead telluride, for example, we can reduce the speed of sound significantly from single crystal values. And as you add more strain, as you add more impurities, the strain also seems to increase, as shown here to the right. But that happens along with the strain, we get a reduction in the speed of sound, which again is very important for reducing the lattice thermal conductivity and ZTs of thermoelectric materials.
2 minutes.
Great. Okay. So in my last minute here, I'd like to just finish with, well, where data science might fit in. So we don't know too much about complex materials. I mean, we've been known about phonons for decades, but it's only recently that we've thought about these special types of phonon modes for complex materials. And I think computational experiments might be the way to do that because there's so much more information involved in such an experiment. So here's, for example, a MD simulation of a structure with a microstructure of dislocation microstructure, which obviously is very complicated. And then thinking about the scattering rate of each individual phonon mode is going to be quite complicated. So to me, data science can help do those calculations as well as interpret them. And to me, the goal is to understand and discover the new emergent physics. So for example, is there really a dimensionality crossover that can help us understand how to engineer both the frequency dependent and the frequency independent terms. For example, the diffusion thermal conductivity could be engineered with these speeds of sound, and engineering the speed of sound then could lead to important new features of thermoelectric and other materials. Okay, and with that, I'd like to thank you, and we can move on to the next speaker.
Okay, thank you very much, Jeff, for the presentation. Again, everybody, please feel free to ask questions through the chat function. We will save all the questions to the end of this session or this afternoon session. So now let's move on to our next presentation by Dr. Amir Farimani from Carnegie Mellon.
Okay, hello everyone. Can you hear me?
Yes.
Okay, great. So I'm Amir Barati Farimani, and I'm an assistant professor in mechanical engineering department at Carnegie Mellon. And today I'm going to talk about, in a high-level sense, about what we can do with artificial intelligence in heat transfer research. So let's talk a little bit about what happened that AI became so much important in the research, especially in engineering and physics. So as you may know, I mean, in 2012, Jeff Hinton gave a phenomenal and seminal paper that they were able essentially to classify 60 million images into 1,000 different categories without doing any kind of hand featureization and automatically, which was superb because, I mean, this is a huge task. As you can see, I mean, there are many complexities with that regard. So the reason that that was so successful was essentially can be summarized into having plenty of data, GPU computing capabilities that became available, new optimization algorithms such as RMS probe and ADAM optimizers, and more important than integration of convolution, which is able to detect the features. So the high level features, for example, the way that human brain is working, and the fact that it is essentially translation rotation invariant. As you can see, it is capable of detecting this cat in these really complex situations. The second revolution that I think, I mean, really helped us to integrate AI was the combination of deep learning or neural networks with the reinforcement learning as an optimization and control technique. And this was another phenomenal paper in Nature in 2015 that they were able to use Q-learning plus function approximation and deep neural networks to perform Atari games. And then after that, you heard about AlphaGo, 0, 1, 2, and all these complex actually control mechanisms in which essentially you can use reinforcement learning and approximate a function using a universal function approximators, which are AKA neural networks. So with these two big breakthroughs in AI, it creates plenty of opportunities for us wherever in engineering we don't have a mathematical or physical description of the system. For example, predicting the thermal conductivity of a complex polymer or monomer is very difficult because essentially the chemistry space and the combinatoric of topology plus chemistry is super huge. You can create 10 to the 60 million molecules, and then predicting all of them via experiment is so expensive. So the solution is essentially to create a training set out of that and very rapidly test and find out, for example, the thermal conductivity of these molecules. On the other hand, very complex manifold of mapping between X and Y can be done with the convolution and essentially the new techniques in deep learning. For example, as you can see, I mean, here is an image and the caption is generated by AI, which is super cool. I mean, this is an image to a text transformation. So wherever we have essentially very complex manifold we want to estimate. So what we can do for AI in engineering, physics, and what are the potentials? So to me, after exploring all these different areas, I think, I mean, wherever we have a complex phenomena in heat transfer that we don't have a mathematical or physical description, the mapping is so difficult that we don't have the physics to describe. The second part is where we don't know the physics of heat transfer, but we want to predict to engineer. We are all engineers, we wanted to predict. So essentially we don't have mathematical model or physics to describe, but we wanted to build things, right? So we need to predict. There AI can be very helpful. Where we want to speed up computation by surrogate fast models, as Jeff mentioned, I mean, we need to create really rapid high throughput screening methods or a smart experimentation, and there AI again can help. And where we have abundance of data from experiments with the rise of sensory equipments, cameras, you know, I mean, heat transfer, basically sensors, temperature sensors, pressure sensors, all what we can do is to make a much more precise model that we have been building, like by essentially creating assumptions in heat transfer. To that end, for example, predicting the thermal conductivity of material, interfacial thermal boundary conductance, predicting those, which needs a lot of computation, creating mapping from thermal camera to the temperature, for example. That's a very complex thing to do. atomistic simulation potential, surrogate model. There are a lot of works in that realm that how we can create a much more effective potentials for MD simulations, density functional theory, computational thermofluid simulations. I mean, you need to build a huge grid for your CFD, thermofluidic simulation. So can we make the reduced order model via dimensionality reduction techniques in neural networks, and essentially discovering physics of heat transfer. So these are the potentials that we can do. And since, I mean, this is only a 10-minute talk, so I can go over a couple of them, actually 2 of them, but these are the 4 areas that I think, I mean, are really, really important to investigate as a future of AI in heat transfer. One of them is system identification in heat transfer, in which you have the spatiotemporal data of heat transport, and you want to essentially build a and understand what is the PDE, partial differential equation, what is the ODE of the system, can we discover the convective term, diffusive terms. The second one is learning thermal conductivity from materials. As Jeff mentioned, we have a complex combinatoric of, atoms combined in a crystal structure or in a kind of organic inorganic setting, and they can be predicted K in a fraction of a second without performing ab initio simulations or molecular dynamics. Heat transfer control in additive manufacturing, it's great, to scale up additive manufacturing, but one of the problems is controlling the melt pool dynamics and how we can effectively do that using AI. And another one, which is much more into the realm of system heat transfer, is even for the HVAC and, the systems that we have for controlling the pump speed or thermal transport speed there, using the sensory data that we have, we get it from Nest or other sensors that we have there, and creating a controller which is robust in that sense. So one of the examples, I'll go over 2 examples from my lab, one of them thermal conductivity for crystals polymers. As you know, the chemistry space is super humongous, so we cannot essentially run MD simulation. So can we build a surrogate model? But the problem for that is, can we develop descriptors or material representation that transform chemistry and topology into numbers? And as soon as you have the numbers as the X vector, then the labels can be, for example, thermal conductivity. To that end, for example, you can create different kind of featureizers like OFM features, neighbor features, and essentially use the graph neural networks, as you can see here, for the OGCNN, and then predict the material properties and benchmark it via other methodologies that you have. Another, the second problem that I wanted to talk about is controlling essentially the laser power to the additive manufacturing using deep reinforcement learning, which was the second revolution that I mentioned. So as you know, when essentially the laser raster is going on and it hits the boundary, it creates a lot of heat accumulation. So we use basically Eagar-Tsai model in order to model the heat conduction and do the simulation for different kind of rasterizing scheme. And the question is that if you have the environment of, for example, your additive manufacturing a part, you're doing the layer by layer build, is it possible to use the deep reinforcement learning in order to control the agent essentially power and velocity of the laser in a way that reduce the variations in the melt pool, which is really bad because it creates keyholes and a lot of defects. So to that end, essentially we created a reward function in which tries to minimize the standard deviation of the melt pool in each iterations. And then this is the state definition that you get from the top, because the observables for us is the heat or the temperature field on the top of the belt. So this is the state definition there. And then essentially one of the biggest problems, especially on the scan pass, is hitting the boundaries and accumulation of heat, for example, here in a triangular setting. And for example, for a horizontal cross hatching, as you can see, this is the way if you wanted to control the velocity in order to have the minimum melt depth variation, which is a cool thing. And as you can see, the velocity is really going high of the laser when you're using deep reinforcement learning, essentially, and then you are able to control the standard deviation, especially for the cases like concentric triangular pass that you are essentially additive manufacture. Especially in the middle, there's a huge accumulation of heat. So turning off that laser is very important. So here you can see there is a huge difference between when you are controlling the velocity and if you are using a constant control strategy without deep reinforcement learning. And you can see the melt pool is essentially very well kept when you are doing the control. But if you don't do the control, you can see a huge variation in the melt depths of the pool. So thank you very much. This is my PhD students in the lab, and this work was done by Francis and Rishi, actually, as the two lead people who work on this.
Thank you very much, Amir. And I would like to invite the next speaker, Professor Payman Givi, to upload his presentation.
Okay. Can I share my screen? All right. Okay, I guess you can hear me all okay?
Yeah.
Okay, thank you. Yeah, my name is Payman Givi, and I'm with the University of Pittsburgh, also a member of the Pittsburgh Quantum Institute. And we have been working on the idea of, quantum computing for several years now. And what I'd like to start this presentation is with the fact that, quantum computing is no longer a fiction. It's something that's there, and we are, as we are with the data revolution, we are also at the stage of second quantum revolution, and quantum computing being a part of it. So what is the thing that we want to do? What is our objective? The objective is to, the idea of quantum computing have been around since 1980s by Feynman. But the thing that we would like to consider is that with all the advancement has been on the development of the quantum algorithm, even though they make sense for quantum system, can we use them for analysis or simulations of classical systems, classical physics, stuff like in heat transfer or fluid mechanics? If we can use quantum computing for that. And this is very important, especially now, because the Moore's law, as many people have said, it has come to its end. I mean, the rate of progress in digital classical computer has come to a stop. So what are the mechanisms by which the quantum computing could be used? I mean, we don't have one universal quantum computers yet, but what are the kind of things that could be used for classical calculations? I had just finished writing a big review article in AIAA journal. I will give you the reference for it, that a large number of classical problems could be considered one of the major effects, and we can talk about more later. One of the major influences of quantum computations is taking advantage of the quantum entanglement for a lot of classical problems. The couple of examples I want to show you are the example that has been published in Aerospace and Combustion journal. One of the ones that we demonstrate quantum benefit, quantum scale-up, is the modeling of mixing and reaction in a plug flow reactor, in which we have reactants coming into a reactor. They mix and they go into the products. And this has been a classical problem in thermal fluid sciences for many decades. It has had a lot of applications, atmospheric and drug sciences, in chemical reactors. And this was one of the issues that we could show that right now with what the quantum algorithms out there, how they can help us with solving this problem. And and with this demonstration, we will show you how we can make use of the current state of progress in any kind of a classical simulation. So the problem that we looked at was this kind of a reactors, and we are using classical probability density function methods. As you may know, PDF methods have been very much in demand in a lot of problems in turbulent fluid mechanics, combustion, convective heat transfer has proven very, very powerful. And the method we had used was, at least with this problem, is a Monte Carlo simulation of this problem that describes the evolution of the PDF by means of some integral differential equations. But basically this method for this problem is a classical problem of mixing, in which have particles of different concentration would mix and produce to some sort of a some sort of a final state. So details of it is not important, but what it is important is the fact that how does the calculations are being done. So this is the way classical computation is done. So this one, if you are doing any kind of this kind of calculations, anything could be on a classical computer. You start with some initial conditions, and then you perform some gate operations, whatever the algorithm you have, and at the very end here, you would read your result. The result, you print them, whatever the solution is. Classically, you know what it is. And if I do the calculations with this particular problem, for example, if I want to show the amount of how much the fuel has been consumed, I can, do the calculation for this case, and I can come up with a figure like this, and my convergence would go as 1 as a square root number of the particle that is done. It's classically known in Monte Carlo processes that your error is proportional to the square root of the number of particles to represent them, and the error being on the right-hand side. Now, we want to demonstrate, okay, so people have been doing it on a quantum computers, how we would do that. Well, if you have a classical computer that we just had, and we have a classical algorithm and classical problem, classical algorithm, and we perform on a classical computer as we are already doing it. Now, what we are right now at the stage that we have a classical problem, but we have a quantum algorithm, but we don't have a quantum computer to make it yet, but we can do the simulations on the quantum computers and show the benefit. There are some cases in which you can show them on a semi-quantum computers, but at least for the problems of this side, while the quantum computers are do not exist, we can show how the results are and demonstrate the quantum advantage. So, okay, how does the process would go? The structure of the case for a quantum computer, we initialize, and this initializations in that form is in a vector space. In a quantum sense, this is the bracket notation that the quantum people use, and we start with that initial state, and we perform the gate operations, that is basically doing simulations of some sort of the Hamiltonian in an equivalent quantum system. And at any time, we have the entire field in a quantum manner. Everything you would know, it is just in a probabilistic manner. And then once we read it, we can learn whatever the values are, and we get, hopefully with a high probability, we are getting the right answer. So that's the idea of the classical quantum algorithms for the time being, performing the calculation in a sophisticated manner, which as you perform the calculation more and more, you get to the correct result. So the ideas would be coming in a quantum computation is that you have the state preparation, and you do the calculations, and then your measurement, how you're measuring, because once you measure it, you affect your result. So how to measure things and how to read them in a quantum things is something that is very something a lot of effort are being devoted to it. So in this particular case, we have been using one of the quantum algorithms that was developed by my colleague, Dr. Rolando Sama at Los Alamos, in which this idea in that business is based on something they call, the phase estimation algorithm, that you want to understand the phase of something in a block square, that one of the building block of a quantum computing. And once you want to measure any of the moments, what you would have, your error would go as 1 over the magnitude of the number of elements. So in our case, when we do this kind of calculations for the chemically reacting flows or for mixing, we would find that you can calculate, I mean, this one is the equivalence figure for the quantum calculations, in which the error goes proportional as 1 over the number of their Monte Carlo element. So if I put everything together, doing the error convergence for the classical and quantum computers shown in here, of course, these are all being done on a classical computer. So it shows that the steep gradient, the steeper gradient of a quantum computer, that shows the benefit for this kind of calculation. And this is just one of the examples. Of course, depending on the quantum computer, this curve could be to the right or to the left. So the concluding remarks is that what is the current practice? Right now they have some analog quantum simulators, as you may know, and there are some hybrid quantum computing that there are no universal, in a sense of universal quantum computers, but some of the computers like D-Waves, they are in the market at NASA Ames Los Alamos, and as you may know, DOE is heavily investing on this business. And what the state of the art is, I mean, the quantum computers with 10 to 15 qubits are not operational, and people are saying that within 100 qubits, it could be there within the next 5 years. And if you are getting to really to 50 qubits, it would be, the quantum supremacy. And I'm going to quote this thing from Nobel laureate Bill Phillips. If these things are actually being done, and I really do think within our lifetime is going to be that, it is going to open up the whole new arena of quantum of calculations. My acknowledgement, what I would like to say that this paper just appeared in AIAA Journal, would give us, we have written, my co-authors from quantum physics and NASA, all of the possible applications of this thing is written on this paper. With that, I close.
And thank you very much again. And for the sake of time, I will invite the next speaker, Professor Philpott, to upload his presentation. Do you mind to unshare your screen? Okay. Professor Philpott, Simon?
Yeah, I'm getting there.
Thank you.
Yeah. So why don't we do that? Okay, here we go. So I'm going to, my background is in atomic resolution type simulation methods, and I'm going to give you a brief vignette of something we did recently, which kind of illustrates the way that this part of the community thinks, and just a very simple example. And then 3 or 4 challenges that I've recognized. Now, one of the disadvantages of appearing after 3 very good speakers is a lot of these things have already been touched upon, so some of this will just be echoing what we've heard before. So the example I'm looking at is something that comes from geology, and it's just the looking at the temperature and pressure dependence of materials in the Earth's mantle. So when you go down into the mantle, the pressure gets high, the temperature gets high. Well, there's been a lot of work done on temperature effects on thermal transport, but there's been less work done on pressure effects. And so what we want to do is to explore this in a representative material. Of that representative material, we chose silica, which is an important material in its own right, and is also kind of representative of the silicates that are so prevalent in the Earth's crust. And so this is some simulation results.
The silica is a hexagonal structure. So we have what we're seeing here is we're seeing in the hexagonal direction and the basal direction, we're seeing the temperature and pressure dependence of the thermal conductivity. So the range here is 20 down to 2. This is kind of the middle range, as we saw in Professor Snyder's presentation. Low thermal conductivity materials are sort of 1 and below. High thermal conductivities are maybe, depending on your application, 100 or more. So these are modest thermal conductivities. We're seeing the temperature dependence here, which is decreasing with temperature as we'd expect, when we see an increase with pressure here. This is a similar result in the basal direction. Temperature goes down with temperature, increases with pressure, and this is done with an atomistic potential. And it turns out this atomistic potential actually gives a very good agreement with experimental values for the Young's modulus, for example. So this seems to be a reasonably reliable potential for elasticity. Whether it's reliable for thermal transport properties is a less resolved question. So how do we kind of understand these? What approach do we use? So this is a version of the standard formula which everyone is familiar with. Thermal conductivity is proportional to specific heat, the velocity squared, and tau, which is the time between scattering events. So we kind of use that as our mantra, as our baseline for understanding a lot of this kind of work. So as we increase the temperature, what happens is we increase the bond length, that's thermal expansion. As you increase the thermal expansion, increase the bond length, the frequencies of vibration tend to decrease. That decreases the amount of heat which is carried by each vibration. That was the amount of tea in Professor Snyder, or coffee in Professor Snyder's cup, was going down. And that has the effect of lowering the thermal transport, lowering thermal conductivity. Another effect is you have more phonon scattering. That is equivalent to having more people carrying cups of coffee around the room, and they're interacting with each other, so their speed, or they're effectively all slowed down. When you have more phonon scattering, that's a decrease in the phonon lifetime, and that also has the effect of lowering the thermal conductivity. So these simple heuristics allow us to explain that temperature dependence in a very qualitative way. Now, if we go to the effect of pressure, this is now showing that same data I showed before, the thermal conductivity at different temperatures as a function of pressure. We can see the thermal conductivity increases with pressure. How do we understand that in terms of our basic level formula? We increase the pressure, we decrease the bond lengths. As we decrease the bond lengths, that's increasing the frequency. The coffee cup is fuller or is larger. That means that we're increasing the heat capacity of the system. Its ability to carry heat is increased, and that's giving us a higher thermal conductivity. So this is a very simple way of understanding these simulation results. Now, those simulation results look very much in the same form as experimental results. And so in that sense, those simulations aren't providing any more information. But we can delve much more deeply into this. We can look at this in various ways. So for example, this is a spectral analysis. This is showing what fraction of the heat transport is carried by phonons of specific frequency ranges. And this is showing it for the hexagonal and the basal phonons. And so what we're seeing here is we're seeing that most of the energy is being transported by these phonons between 1 terahertz and maybe 5 terahertz. So a lot of these are the acoustic, a lot of this region here is the acoustic phonons that we saw in Professor Snyder's presentation. But what we're seeing here, maybe above about 5 terahertz, is the contributions from the optical phonons. And in this case, these optical phonons are providing roughly half of the contribution to the thermal conductivity. And we can see here, this is the dashed lines are the accumulated values of that. And you can see here that the accumulated values, that there's a different dependence, that depending on which direction you're going in, you have more contributions at lower frequencies than higher frequencies. So here this is saying that the frequency range which is contributing to the thermal conductivity actually depends on the direction of thermal conductivity.
2 minutes.
Crystallographic direction. So opportunities. The opportunities I see are increasing the precision of calculations, looking at complex microstructure, what I call phonons plus, which is adding other excitations to the phonons and getting more information about scattering mechanisms. So this was covered by Professor Snyder, and one of the other talks mentioned this, which is increasing the precision of interatomic interactions. And so I think the frontier here is using AI for machine learned potentials. So taking electronic structure calculations, which are slow, taking the results from those to develop machine learned potentials. This will have two advantages. They will be more accurate. Here's some computational results using a machine learned potential. Can give more accurate results than traditional potentials, but also will enable us to more rapidly develop potentials which can look at more systems more quickly. So there's one area. Complex microstructures, that's also come up before, there's relatively little, there's not a unified understanding of the effect of microstructure on thermal transport. And I think there's big opportunities there to look at those. I won't say any more as I'm running out of time. Phonons plus, phonons interact, there's electron phonon interactions, there's magnon phonon interactions, there's phonons interacting with other excitations and structures in the system, and a lot of that is not very well explored to this point. Finally, the scattering mechanisms. This is actually a very old image from work I did a long time ago. And this is showing a scattering event of sending a phonon package on the top line into scattering into some sort of boundary. And what we're seeing here is we're seeing the parts which are reflecting and the parts which are transmitting. So this first part is basically acoustic model type scattering. This is diffuse type model scattering. And this is a direct indication that these classic approaches are both useful, but are both limited also in that they don't describe this interaction. But we're getting a lot of information here on the scattering event out of this particular defect, the structure which I haven't defined. But I think there's opportunity here to parse this information, perhaps with using AI methods, to have a much better understanding of scattering mechanisms. And these scattering mechanisms are what really contribute to the fundamental process of thermal conduction at microstructural, various microstructures. And we need to resolve those. So that's what I have to say today.
Okay, thank you very much, Dr. Philpott. Now let's welcome our last speaker for today, Dr. Austin Minish from Caltech.
Hi, Simon, if you can stop sharing. There we go. Yep.
Oh, yeah. I do it.
All right. Hopefully you can see that. And let me, okay, hopefully that looks all right. All right. Thanks very much. Again, I'm Austin Minnick at Caltech. I wanted to thank the organizers for giving me the chance to speak here and thank them for doing all this twice. And I have a conference that I was helping to organize that was supposed to occur in the summer, and now we're trying to essentially do it over again too. So I know how much work it is. So thanks again. Today, I'd like to tell you about our work on ultra low noise transistor microwave amplifiers, which have many applications, but including for quantum computers. And so, we are interested, of course, like one of the other speakers, in applications of quantum computers, but today I'd like to focus on the hardware challenges. So just very briefly, these amplifiers are particularly of use for superconducting qubit quantum computers. So I just want to very briefly tell you approximately how they work. So if you have a superconducting metal, you can arrange it into this resonator, LC resonator on the left, and this is just a regular harmonic oscillator, and it has these equally spaced energy levels. For a qubit, you only want to use the lowest two energy levels. So this harmonic oscillator is not very useful. But if you add a Josephson junction to it, in the that X there in the circuit, then you have this anharmonicity, which creates a difference in the different energy level spacings. And so you can use the bottom two as the qubit. And after lots and lots of development over primarily in the modern era, the past 20 years, you can create these devices that look something like this. And we don't really care so much about all the details, but you can deposit metal in a particular way, and you can create these inductors and capacitors and Josephson junctions and so on that make up each of the individual qubits. And you can figure out how to couple them together to make the computer do something. So one of the important tasks, as was mentioned by one of the earlier speakers, is of course you have to read out the state of the qubit to extract information from the quantum computer. So the way that you do that is, if you start on the upper left of the slide, you send a microwave tone along a transmission line, and it reads out the state of the qubit with some particular way, and we'll just assume that somehow it does it. And then it goes to a circulator to prevent radiation going backwards down the line. Oh, sorry. Trying to advance the slide. Okay, there we go. So, and then, this tone is extremely weak in energy, because otherwise it will disturb the state of the qubit too much. So you have a number of amplifiers along the way. The first is this Josephson parametric amplifier, and the second one is this high electron mobility transistor. And that's what I'm going to talk to you about today, is the noise figure of these HEMTs, as we call it. So here's a picture of one, and it's a standard field effect transistor. So you have a source and a drain, and then you apply the signal, the readout tone for the qubit between the source and the gate. And if you look in here, the reason they're high electron mobility is there's this 2D electron gas in that channel, and it has very, very high mobility. Okay, so again, you apply this readout tone to the source gate terminals, and you apply the VDS across the source and drain, and you get an amplified signal out of that. And of course here, the goal is you want the lowest possible noise. So to understand the noise mechanisms, there's two main ones. There's the fact that the gate is a metal at a certain temperature. So there's thermal fluctuations and hence Johnson noise in the gate metal, which affects the current going through the channel. Then there's also what's known as hot electron noise, which occurs, it's the noise that's associated with a hot electron gas moving through a semiconductor. So, the goal here is to understand the physical origin of these noise mechanisms and try to eliminate them as much as you can. And just very briefly, to give you an idea of the state of the art, the red line is the quantum limit for any linear amplifier, and that dashed black line is 3 times the quantum limit. And most amplifiers, the ones that are available in the kind of 4 to 8 gigahertz range at the left of the plot, are somewhere around 4 to 5 times the quantum limit. So the question my group's trying to ask is, can these microwave amplifiers operate at, or at least closer to, the quantum limit? And it's here that transport phenomena play an important role in answering this question. So some time ago, we did these experiments where we're measuring the noise temperature versus the physical temperature of the amplifier. And you observe that there's this discrepancy at low temperatures where the noise temperature is supposed to be something less than a Kelvin, but it actually saturates instead experimentally to something around 3 or even 4 Kelvin. And of course, this is a significant problem. So we thought about this, and eventually we think we've figured out that the origin is due to self-heating. So at cryogenic temperatures, as many of us know in this community, heat conduction occurs by phonon radiation rather than by diffusion. And so the phonons are being radiated out from this hotspot, and those hot phonons are impinging on the gate metal and heating the electrons, and the electrons then exhibit this thermal noise. And so that's what I'm trying to convey here is rather than diffusion at 4 Kelvin physical temperature, the self-heating can be quite substantial, order of 20 Kelvin. And so that means the gate metal itself is not at the same temperature as the physical temperature of the amplifier. Okay, so that suggests mechanisms to try to mitigate it. The not particularly elegant way, but in principle should work method is to use the boiling of liquid helium to lift heat from this gate and thereby decrease its physical temperature of the gate metal. There's some interesting heat transfer problems that occur when you try to experimentally do this. One of them is that liquid helium boiling has been extensively investigated in the 70s and 80s and even before that. And it's known that there's a limited peak heat flux for the superheat of any surface. And this limited heat flux is actually many times smaller than what's required to remove the heat flux emanating from the gate. The possible solution to this is to use the very special phase of helium, which is the superfluid phase. And that phase is actually widely used in superconducting colliders to cool the magnets at 4 Kelvin. So that's a known strategy to do this cooling, but it's not ever been applied for this particular problem. So there's some interesting applied research to understand to what extent this will work in decreasing the noise figure of these amplifiers. The last thing that I'd like to talk about is that second noise mechanism, which is hot electron noise or drain noise. So as you apply a bias from source to drain, you drive these electrons through the channel, and there's of course, this electric field, which has the secondary effect of heating the electrons. And as the electrons therefore go through this channel, they could be hundreds or even thousands of Kelvin hotter than the lattice. And there's noise associated with that process beyond just thermal noise, because electrons in these heterostructures can jump from the channel to the barrier and leading to what's called partition noise. They can go from the central valley to a satellite valley in the reciprocal space, which is known as inter-valley scattering. So it gets rather complicated.
1 minute.
Okay, thank you. Yep. So just schematically, what's happening is you have an electron going through this channel, and there's some type of event that causes it to change its wave vector. It's a state in the Brownian zone, and those fluctuations lead to noise. So velocity fluctuations about a steady state lead to this current noise that's observed at the output of the device. So this type of problem stimulates efforts to understand high field transport in semiconductors without requiring assumptions regarding the scattering mechanisms for electron phonon scattering. And that is indeed possible. And due to time, I'm not going to go into all the detail, but we have this Boltzmann equation, and we know now how to compute the phonon mediated scattering elements for this matrix. And the low field calculation is now a standard procedure. What we've recently done is extend this to high fields, and we've also figured out how to compute electronic noise rather than just a low field transport property. And so this is a recent result, which is a step on the way to understanding this drain noise. So what I hope I've conveyed to you is that there are many, many engineering challenges associated with simply building a quantum computer. And one of them is the instrumentation has to operate really at the physical limits. And so in order to reach those limits, it's important that we have to understand and apply transport physics to mitigate these noise mechanisms. So with that, I will conclude, and thanks again for the opportunity, and look forward to the next section.
Okay, thank you very much, Dr. Minish, for your presentation. And again, we would like to thank all the panelists for their presentations. So now we will move on to the question and answer session. So first, I would like to raise a question from the moderators to all the panelists. We would like to know your vision of artificial intelligence in future thermal transport research, and more particularly, can we really mine essential physics of thermal transport phenomena from these methods instead of just obtaining thermal properties like thermal conductivity from machine learning, all this stuff. So panelists, feel free to unmute yourselves and answer question. Thank you.
So maybe I can start here. So I think, artificial intelligence can help us a lot in heat transfer research, especially there are part of research that we don't have, as I mentioned, like mathematical or physical description. We don't have a partial differential equation for that, or the manifold is so complex that essentially we cannot predict the phenomenon. Examples of that, as other speakers actually talked about, is, for example, predicting the organic molecules thermal conductivity, or a crystal structure's thermal conductivity. And about the second question, that can we learn the physics of transport phenomena using AI and big data? The answer is yes. I'm going to put the paper that we recently gave that we are learning the partial differential equations, convective terms, conduction terms, diffusion terms from the spatiotemporal data. It is completely possible because if you think about it, convolution operation, which is running on the data, is a kind of feature detectors. And as soon as you were able using basically detect the features that are associated with a physics, then you are able to detect those features and connect them to the physical properties or equations that you want.
Okay, thank you for the answer.
Can I add something to it? Yeah, this is Payman Givi. One of the things we had done last February, we had to organize a workshop for NSF with Ron Joslin and Shahab Shojai. We organized this conference and it was, the idea was machine learning, the idea of machine learning for transport phenomena. And, the report for it is being published now, but, there were several ideas that, many of the speakers talked about for how machine learning and to some extent artificial intelligence could be used for advancing the problem thermal transport. One of the things that I find, and I found it very useful for a lot of phenomena that are governed by ill-posed differential equation or inverse problem. That is one of the major advantages that happened with machine learning. You can investigate those problems. And also, one of the other things that a lot of people felt there was that, a lot of the physics informed machine learning, in which all of the optimization techniques that you have is kind of being enhanced by the physics of the problem. Could it be heat transfer or mass transfer or whatever it is? The governing equation becomes one of the parameters of the optimization. So something that we can discuss more, it is just more and more now that we are basically on the second wave of machine learning, is that we're bringing more and more of the physics into the picture is deemed very important.
So Amir, would you describe your result that you talked about, a physics-based model where you're using machine learning to get the parameters for the physics?
Yeah, exactly. I just shared the archive paper that we are able to essentially detect the features. So you can essentially use the featureizer. Like, you can, for example, you do the discretization, right? When you're solving a heat transfer or PDE problem, right? You discretize the domain and then you discretize the equation. So the reverse of that is possible. So what you can do is essentially, for example, if you want to see that this spatiotemporal phenomena is satisfying, for example, the Laplacian form, right? Or the conduction equation, then what you can do is to featureize that using, for example, subtracting each node points from each other and see if there's a residual with respect to 4 nodes being the average of the middle point for the Laplacian equation. And if there is no residual there, essentially you can say that, yeah, this term Laplacian is existing there. A much more detail about that is in the archive paper that I just shared that my PhD student Kazem did. And essentially you can extract all these relevant PDE partial terms. For example, the first derivative with respect to time, the second derivative with respect to time, the derivatives with respect essentially to the space, and assemble them using, for example, classical, even shallow machine learning algorithm like XGBoost or random forest. It doesn't need to be a like super deep learning classical model. So I think, I mean, it's possible to detect, I mean, these features and assemble like the PDEs, I mean, to discover some of the dominant modes. Essentially, it was very difficult for us to differentiate between convective transport and conductive transport, especially when the thermal boundary conductance and convection actually is in a very low Reynolds number. So these are really details that you need to consider there.
So are you using computational input? So a simulation?
Yes, you can generate, we generated hundreds of different types of PDEs in this work that is here. And then the big thing about this work is that we are able to detect new PDEs. So essentially out of class prediction, because if you already show the physics, it's not an art to find out that physics or rebuild it. So we put completely, for example, convective diffusion equation class out, and then this is able to detect the terms of that, like, I mean, if there is a U sub t or U sub tt, and then assemble them together to find out that PDE. Yes, but simulation is simulation data.
Right, so it's a simulation data. So there's already underlying physics that govern the simulation. But what you're telling me is that you're using machine learning to basically extract the emergent phenomena that comes out of it.
Yeah, exactly.
Even though it's essentially simulation data.
Simulation data, you can put the complete class of equation out, not training it, and then see if it is able to assemble the terms to get that phenomena. It's like, I mean, Poisson or Laplace or Navier or Stokes, that they were sharpening their pencils and trying to derive the equations. So I think my AI can do that now.
Mm-hmm. Mm-hmm. Yeah. So, so one of the things that we work with is, we work with machine learning folks who want to take experimental data, and our experimental data set is obviously, not as detailed as a simulation data set. And so if you only have, for example, thermal conductivity values at room temperature, or even as a function of temperature, just some scalar number for a single sample, there's not really a whole lot of machine learning that you can do with that goes beyond our understanding of the physics. But if you're saying what you can do is machine learning of a simulation, so if we have a simulation of some complex structure where we have all of the individual atom motions, but we need a way to digest that into some emergent phenomena with a Navier-Stokes type equation, then I think, yeah, there is a huge opportunity there.
There's a huge opportunity there. I totally agree with you. And I know that there are a lot of efforts on prediction of atomistic simulations, building machine learning potentials for thermal conductivity, essentially predicting like defective sites, what will happen if, for example, you have MOS2 or graphene, you remove a couple of atoms there, or like other crystal materials, can we predict those type of things? So I think, there are a lot of
sorry, I have to cut in. So because we are running out of time, we need to ask everybody to join the poster session now. So probably we can stop now and restart all these discussions in our afternoon session.
Sure.
That's great.
Okay, thank you. And thank you everybody for attending this morning session. And we will see you at 1 p.m. today for further discussions with the panelists.